So today we are going to learn TimSort. Okay. TimSort is the most advanced sorting algorithm, and it is used in all the major programming languages like Python, Java, Rust. Okay, when you call the inbuilt sort program given a array list dot sort, then actually it is called TimSort. It was developed by Tim Peter it was implemented by Tim Peter in 2002 for the Python sort program the first time, but it was actually developed by McElroy in 1986 in his research paper. Now let's see how it's work. TimSort actually works on the with the help of two well-known sorting algorithms we covered in the last class, merge sort and the insertion sort, which I have not covered, but it is very simple and obvious. Okay, so those who have forgot the things, insertion sort is it's basically a given array. Okay, and we use two loop. The first loop, loop one, it is incremented from starting point to end point of the array. Okay. And let's say this is the intermediate position, kth position, okay. And this first loop is at k. So we use a second loop in this way. What we do, we start this first loop from the first position and check. For first element we do nothing. For second element we check. For example, this k at the moment, let's say this k is second element. So what we are going to do, we'll check whether the element inside this kth position is smaller or greater. Okay, if it is smaller, left side elements are smaller, then it is okay. If it is not smaller, then we have to shift the element one place at the right, and this kth element will be placed there. So this process will continue. So at the intermediate level, suppose the loop 1 is at kth position and this is loop 2. Okay, loop 2 is basically looking for the previous element, whether the previous element is smaller or not. If smaller, then okay. If it is previous element is not smaller, then it will check to the previous element will be shifted in right side one place. Then before that we have to shift in this way. So sorting basically inserting the element in its proper position, just like sorting the deck of cards. So that is insertion sort. And merge sort. Merge sort is basically it's mostly about the single function merge function. What merge function do? It take two sorted array, let's say A1 and A2. Both the array are sorted array. Okay. So I can write that A1, A2. Okay. And the output of this program is also sorted. Okay. So one thing to remember that when implementing this merge function A1 and A2, both the array are sorted and the output is also sorted. We have to take care of one thing. What is the size of A1 and A2? If they are equal, we are going to get the complexity lower. If they are not equal, for example, let's say I have an array of element, okay, and I have started merging on the left side. This is the first element. Let's say the elements are 2, 5, 3, 1, whatever. Okay. So let's say I have taken first array as the first element as the A1 and the second element as A2. And both are singleton set, and there is nothing to sort, so both are sorted. So we can run this inside the merge function and we can merge it to one array. Looks like one array of size 2. Okay. If I merge this with the third element, then it will be merged and 3 will be in between. Okay. Merge function will make these 3 at the place of 5, and 5 will be 6. Okay. So if we continue this merge function in this way, okay, then what will happen? Every time we are merging with a large array and a single element, then the complexity will go to what? It will be nothing other than insertion. That will be complexity of n square, worst case. Okay. So the beauty of merge sort work when the array size are almost equal. Okay. If the array size are not equal, then the merge function, the merge sort program will not give us the nlogn complexity. Okay. In our merge sort program, we every time divide it into two equal parts, so this problem does not appear. But it is important in TimSort because we have a different. Now let's start with the TimSort. How TimSort? Okay. Suppose we are given array, long array. Now I am writing the all the elements. Let's say we have 13, 5, 2, 7, and very long. It may be, does not matter. 9, 12, 21, 45. Okay, in this way. Now, first step, what uh, TimSort algorithm? I have started TimSort from here. So let's write Tim. So what we will check? We have to check the runs. Okay, we call it run. Monotonic run. Okay. So let's say 13. 13, then 5. 5 is smaller, then 2. 2 is smaller. Okay. So this is a run. 13, 5, 2 is a run, but this 7 is not included in this run. Okay. 7, 1 can be a different run. Okay. 9, 12, 21, 45 can be a different run. So some runs are bigger, some runs are smaller. Okay. There are many algorithms to find run. For example, in some other lecture, I will tell you how to find peak inside a given sequence, peak and valley. Okay. So if we can find peak and valley, then we can easily detect this run. But for our case in TimSort, we don't need to go for that peak and valley. What uh, we have a minimum run size. We have a concept of minimum run size. Okay, we have a concept of minimum run size. So let's say it's generally in the Python program, it's generally 32 to 64. It's any value that depends on what input we are taking. Based on that, this value is generally 32 to 64. Okay, it may be 35, 40. So a minimum run size is fixed. For the timing, let's assume that the minimum run size is 30. So what we will do? if we have a long sequence of array, we will create a run size of minimum 32. If a monotonic sequence like increasing or decreasing of more than 32 appear, then it is fine. It is considered as run. If the monotonic sequence goes up to, let's say, 40 element and our minimum run size is 32, then it is fine because 32 is minimum run size. Okay, run may be bigger than that, but run cannot be smaller than that. If we have a run of, let's say, 25 element and our minimum run size is 32, so what we are going to do? We will include all the 32 elements inside the run where 25 elements are already sorted and remaining 7 elements are not sorted. So how we will incorporate those remaining 7 elements? We will take remaining 7 elements from the sequence and go for insertion sort to fix this, make them sorted. So every run is sorted. If the run length is more than minimum run size, then it is naturally sorted in the given data. If run length is less than 32, then we'll make it 32 because of this minimum run size constant. And when we will make it 32, some element will be not sorted. We'll go for insertion sort to make it sorted. Okay. So let's write the algorithm parallelly. TimSort algorithm. What we have to give? We have an array like all other sorting algorithm, and the first element of the array and the last element of the array equal, and now the first step is decompose sequence into runs. Okay. So this runs is also a variable. We store these variables. Runs is basically collection of all the runs. So they are sub-array, many sub-array inside this. Okay. So these runs contain many runs. All those runs have some length. They are more than 32. For some case, it may be 40, 50, it may be 100, 200. No matter if there is a continuous run inside the given data of 200 size, that is fine. Run length may be that, but all these runs are short. Okay. Now, next step, the concept of run is clear. So we are creating sorted subarray using insertions. Now run set created. Now what the next step? Next step, we have to take a stack. Let's say the stack is named as R. R is the stack. Okay. Now there is a loop. We may take while loop. Okay. While R not equal to empty, we have to do continue. Yes. So the stack is until it is non-empty, we will continue. What we will do? We will check whether there is okay, runs are denoted inside the R as, let me draw the R. Let's say this is our stack. Okay, R. This is our stack R, and there are many runs inside the stack. We'll start counting from the top. Let's say this is R1, length 35, R2, length 56, R3, length 201, okay, R4, length 72, okay, in this way. This is called R height. This length is called R height, the height of the stack. So this is run height, and it start counting from the top. Now inside while loop, what we have to do first? Okay, I missed one step, that this run should be taken to the stack. Okay. All these runs should be taken to the stack. Okay. So what we will do? It actually, no, not directly. It actually we take the runs sequentially inside R. Okay. So here we have to put some run inside R. Okay. Let's say we have taken R1, initialize stack. We have to initialize the stack with at least one, otherwise this condition will not. Now first check is if number of runs in R less than equal to less than 2, then okay. So we need more than 2 runs inside R every time. Otherwise we cannot do any operation. Okay. When run size is 1, we will return this. So we will insert more runs in the R, and now there is a function called merge collapse. Okay. But before going for merge collapse, we have some condition. Okay, rules for selecting runs from merge. So how to select the rules? Suppose I have 4 runs. So we will start counting from the top. What are the minimum runs? So R35 is the small run, then R56 is also small run. R3 is 201. This is a bigger run. Okay. So what we have to do? We have to, in this case, the condition is we have to merge these smaller runs R1 and R2. Okay. So in this way, there are many set of rules, a collection of rules. Look at the top three, then look at the top four. Which one are the minimum? So ultimate objective is that the two minimum runs will be selected for merging. And merge operation is written here as merge collapse. Okay, merge collapse, and you will put two run Rx and Ry. So what merge collapse will do? Merge collapse will merge because both the runs are sorted. So it will merge Rx and Ry and create a new run into the stack. Okay. In place of Rx and Ry, it will create a new run. So that is merge collapse function. Now these things will be continued. These things will be continued till all the runs are merged and when okay, so this is a loop, this will continue. When this loop is over, when one run, then when one run, then return. Okay, so this is the final sorted output. Now there are many rules. Okay, there are many condition if else if x r1 greater than r2 then r3. Okay, so but the moral of this rule set is selecting the two runs. Now how the complexity work? Complexity work in this way when we are creating these runs. Okay, following the minimum run size, there is a violation. Okay, there is a violation of continuity. Okay, monotonicity. There is a violation of monotonicity, so we force the element to get into the one run. Okay, and we use insertion. Okay, so the very few elements are basically sorted using insertion. So it's being actually the very near to the lower bound of the insertion sort, that is order of n. Okay, when we are writing lower bound, we use omega c. So the creation process of run, it gives us the order of n lower bound, and this rule is very important to maintain nlogn. Why? Because if we do not merge the equal size of runs, then it will violate the nlogn condition. And there is the information theoretic proof recently published in 2018 that this stack merging through the stack will give us the nlogn complexity. Okay, that is same as merge. Now there are some more concepts which we can use in normal workshop as well. One is galloping. Galloping. So let's take an example. When we are merging two sub-array into a single array, let's say this sub-array is 2, 4, 6 and 10, 7. And this sub-array is 1, 3, 5, and then 8, 9, 10. Okay. So galloping thing is when we are merging, let's say this is continuum. Okay, there are many more elements. Okay, and there is also many more elements. So galloping thing occur when suppose we are at 1, 3, 5, and this is 7, and the next element is 7, maybe let's say 25. Okay, so when we are merging two subarray, we take two pointer here. We'll start from here in the first subarray, start from here from in the second subarray, then we have the output subarray. Okay, so which one is minimum will be written in the math function. One, this output array, one, then it will be two, then it will be three, then it will be four, then it will be five, then it will be 6, 10, 7. Okay, then it will be 8, now 9, 10. Okay. So what, when we are merging this thing, we are basically checking every position whether the element is bigger or not, which one is smaller, sorry, which one is smaller. So if instead of doing in this way, we continuously check 8, 9, 10, 11, and not checking the, not incrementing the value here. We are continuously checking here and then increment one place here and check. If still it is smaller, it means all the elements before are smaller. So we can write the whole chain at a at one in the output circuit. So this method is called galloping. Yes, instead of checking every element one after another, we can skip some element and check some point. If that is still minimum, then all previous elements are minimum. Then we can write at one way. So this method is called galloping. This can be used in merge sort also. In TimSort, team merging, this galloping is very rampantly used. So this is almost uh, all about TimSort. Now you can implement this, or you can uh, go through the ready implementation by Tim Peter. So there are some many things they are doing inside the code. There are very small things, and some part can be run in parallel also. So if the disk file is uh, we have disk file to sort, then we can go for this, think about this minimum run size. If that fits inside a single block, that will be fine. Okay. So there are many issues related to this, but I think I have given a good understanding of this TimSort. And remember this, this is the most efficient sorting algorithm exists and used in all the programming languages. Before that, quicksort was used, but it has basically removed the quicksort and taken the fast place. So that's all.